Hello everyone, welcome back. In this particular video, we're going to focus on the chemistry of esters. Esters are another class of carboxylic acid derivatives that have the general formula of R C double bond O O R prime. Okay, so there are the acyl carbon and the oxygen here, they are both connected to carbon containing groups. The acyl carbon could also be connected to just a hydrogen. Okay, that is fine because then that would be a formic ester. That is a possibility. And what we're going to do initially is look at the synthesis of this class of molecules. How are these molecules synthesized? Now, all known methods for synthesizing esters, or at least all common methods for synthesizing esters, they are based on carboxylic acids. Carboxylic acid is the starting material for synthesizing this class of compounds. One possibility here is to take the carboxylic acid and then react it with a base. So an example being sodium hydroxide. Since you have an acidic proton here, when you react the carboxylic acid with a base, it will convert the carboxylic acid into the carboxylate ion. Okay, so you get a carboxylate ion, which is the conjugate base of the carboxylic acid. That's what the carboxylate is. And now once you have the carboxylate, if you look at the ester molecule R prime, you have to just add an R prime or the other carbon containing group to this oxygen. So you could simply do an SN2 kind of reaction to make that bond. So you could take the carboxylate, and if you attack an alkyl halide, you would do an SN2 reaction, and that would convert your carboxylate ion into the ester molecule. So notice we make the ester that way. Now, since this last step or the second step here is an SN2-like reaction, what that means is that all the conditions that apply to SN2 reactions, they would apply here. So this reaction would work best with methyl halides or primary alkyl halides. And it's not going to work with tertiary alkyl halides because tertiary alkyl halides are not good substrates. They are not good substrates for an SN2 reaction. Okay, so that's the synthesis. That's one synthesis starting from carboxylic acids. A second approach to synthesizing an ester from a carboxylic acid would involve the acid chloride. So you can convert a carboxylic acid into an acid chloride by reacting it with thionyl chloride. And once you know, once you make this the acid chloride, you can then react it with an alcohol in presence of a base, pyridine being the most common base. Now, sometimes you would notice that a base may not be involved, but excess of the alcohol is used, and that would work fine here too. But the base would make the overall reaction more efficient. Okay, it's going to push the reaction forward. So you could react the acid chloride with an alcohol in presence of a base to again get your ester. So you can synthesize the ester that way. Now, so both of these methods, they start with the carboxylic acid and they convert the carboxylic acid into some intermediate, whether it's the carboxylate ion, which is the conjugate base, or the acid chloride. And then you go ahead and make the ester. The most straightforward and the simplest synthesis of carboxylic acid esters, or esters in general, involves a direct reaction of a carboxylic acid with an alcohol. This reaction is catalyzed by acid, so sulfuric acid or para-toluene sulfonic acid, one of those acids can be used. And this reaction converts the carboxylic acid and the alcohol into an ester. Overall, this reaction results in the loss of a water molecule. So you can view this as a dehydration in some sense. You're losing a molecule of water between the carboxylic acid and the alcohol to get the ester molecule. This reaction, which directly converts the carboxylic acid and the alcohol into an ester, is called the Fischer esterification reaction. What we're going to do next is look at the mechanism of a Fischer esterification. The mechanism of a Fischer esterification starts by an initial protonation of the carboxylic acid molecule. So when you have a carboxylic acid and when you're reacting with an alcohol, and I'm using para-toluene sulfonic acid, catalytic amount of that acid, we do not need a lot of the acid because the acid would be regenerated in the end. You would get the ester molecule plus water. So the reaction starts by the protonation of the carboxylic acid. Now, like any other carboxylic acid derivative, the carboxylic acid molecule is basic and nucleophilic at the acyl oxygen. So that's what gets protonated. Now, what I'm going to do here is, for the purposes of the mechanism, I'm just going to use HA to represent an acid. Okay, that's the H, the proton in the acid. So the mechanism starts by an initial protonation. So the acyl oxygen gets protonated using the acid that's in your reaction mixture. And this would give us the protonated carboxylic acid. So the carboxylic acid is now protonated. Okay. Once the protonation is done, the next step in the mechanism is the attack by the nucleophile. Now, relate this to other mechanisms of carboxylic acid derivatives or carboxylic acids that we've seen under acidic conditions. So under acidic conditions, the first step is always a protonation, and then the second step is the nucleophilic attack. So this protonated carboxylic acid now gets attacked by the alcohol molecule. Okay, so the oxygen uses its lone pair to go and attack that acyl carbon. Simultaneously, the double bond here opens up to push electrons to the oxygen atom. And this would bring us to our next intermediate, where we will have the carbon here. What was the acyl carbon would now be connected to two hydroxyl groups. Notice the double bonded oxygen with the hydrogen on it becomes another hydroxyl group. And we would have the alcohol connected to that carbon through using the oxygen atom. And the oxygen would have a formal charge on it. Now, like with any other mechanism, always keep focus on the target. Where are we going? Okay, so if you look at it, to go from this intermediate where we are now to the product ester, what we need to do is we need to deprotonate this oxygen here. We need to remove this hydrogen. Okay, that was R prime. So we need to remove that hydrogen, and then we need to get rid of one of the hydroxyl groups here and put a double bond back. So since we need to deprotonate, the next step here is going to be the deprotonation. And since this reaction is usually done in the presence of excess alcohol, which means you use the alcohol as your solvent for the reaction, what we can do is we can use the alcohol for the deprotonation. The alcohol can act as a base. And again, recollect from SN1 chemistry that the alcohol can serve as a weak base as well as a weak nucleophile. So the alcohol molecule can use its lone pair on the oxygen to deprotonate this intermediate that we got. And it would bring us to the next step where we have OR prime, two lone pairs on that oxygen, a hydroxyl group, and hydroxyl group. Now, also notice that I'm drawing each step as a reversible step, because if you think about it, each of these steps is reversible. We are protonating the acyl oxygen in the first step, but we will make A minus along with it. Okay, the A minus can go ahead and deprotonate, and it will bring us back to the carboxylic acid. Or when the alcohol attacks, you push up the lone pair, but a lone pair from this hydroxyl can come back down and push out the alcohol. So you can go back and forth. This is just an acid-base reaction, a deprotonation. That's also reversible. So we get to the next intermediate here. And along with this, we will have our protonated alcohol. I'm going to draw it out because we need to use the proton again. So I'm going to draw it as R prime, OH, H, one lone pair, and positive charge. And now, since we need to get rid of one of these hydroxyl groups to get that double bond, what we're going to do is we're going to protonate one of these hydroxyl groups. Again, which one you choose is irrelevant. There are 3 oxygens in this intermediate. In principle, any of these oxygens can get protonated. If the ether oxygen here with the OR, if that gets protonated, that brings us back to the previous intermediate. But when one of these 2 hydroxyl groups get protonated, it will move the reaction forward. So it gets protonated, electrons move to that oxygen again, and this will bring us to the next intermediate here, where we have R, O, R prime, going to have OH, and then an OH2, lone pair, positive charge. So notice what we've done is we've converted one of these hydroxyl groups into a good leaving group. And along with this, we're also going to get our alcohol back from there. Okay. Now we are really close to the end of this mechanism. What happens in the next step here is that the oxygen lone pair can come down from the hydroxyl group. The lone pair can come down, and it can push this water molecule out. And you get to the next intermediate where you would have R, C double bond O, OR prime, hydrogen, one lone pair, and positive charge. We're really close. We are at the protonated ester right now. Okay. Now, what I did here is I used 2 electron pushes simultaneously to get to this protonated ester. And along with this, we are going to release water molecule. That's this water molecule that's coming out over there. Okay. Now, you could, in principle, split this electron push into 2 steps. Okay. So if I draw this molecule again, what we are looking at is OR prime, hydroxyl, and an OH2, positive charge. So let's say if I don't want to push 2 electrons or don't want to show 2 electron pushes at the same time simultaneously, I can split them up. Because we have a good leaving group here, the OH2, okay, the hydroxyl, which has become the OH2, what we can do is we can just say that, okay, this water leaves. That's a good leaving group. Under the reaction conditions, it leaves. And plus this reaction, again, a little bit more detail, this reaction is usually heated. You will do this with heating. Okay, it needs some energy for the reaction to occur. So the water molecule leaves, and this will bring us to an intermediate where we would have OR prime, we'll have hydroxyl group, and there would be a carbocation on that carbon because the water molecule left from here, so there should be a carbocation. And now if you look at this intermediate that we made, if we do resonance on this intermediate, it will take us to this other intermediate that we have. Okay, it will bring us to this other intermediate. And so you could do it stepwise, or you could show the electron push in one step. And essentially from this last intermediate that we have here, if we use an alcohol molecule again, a molecule of alcohol can deprotonate this intermediate, put the electrons down. That would bring us to the ester. So that's the complete mechanism of a Fischer esterification. Important thing to note is that the initial protonation happens at the acyl oxygen, and then the alcohol attacks the acyl carbon. And what you should realize as you work through the mechanism, if you track it, notice that the oxygen that's coming from the alcohol, that is what ends up as the ester oxygen in the product. It stays throughout, okay? It is there throughout and finally becomes the ester oxygen. So the hydroxyl group in the carboxylic acid, in a very broad sense, is what's lost as the water molecule here. Now, since this reaction is completely reversible, every step in the mechanism is reversible, what that means is if you can go forward, you can also come back. That means if you take an ester with water, and if you add acid to it, and if you reflux it, if you heat it, you should be able to hydrolyze the ester and come back to the carboxylic acid and the starting alcohol. Okay, and so that could be a problem as far as the reaction is concerned. So when this reaction is done, the Fischer esterification is done, what you have to do is to push the reaction forward. What you would have to do is you would have to remove the water, okay? Remove water, or you could remove ester, one of those two components, okay? It could be water or it could be ester. You want to remove one of those components so that you can push this reaction forward by Le Chatelier's principle. When one of the products is going to be missing, then the reaction would be pushed forward. Okay, so that's the Fischer esterification reaction, the most straightforward reaction for synthesizing esters, starting from a carboxylic acid and an alcohol. Next, let's look at some examples of Fischer esterification reactions. So I have basically a few examples here to represent like various possibilities here. So let's say in the first example here, we have working with benzoic acid. So it's a carboxylic acid that's based on benzene. You're reacting it with ethanol in presence of para-toluene sulfonic acid, and you're heating it. So under these conditions, carboxylic acid plus an alcohol in presence of acid, that would give you an ester. So the ester product can be written by putting down the structure of the carboxylic acid, draw until the acyl carbon, or the acyl group, sorry, draw until the acyl carbon, skip this hydroxyl group, and replace this hydroxyl group with the oxygen and the ethyl group from here. Or the other way to think about it is remove this hydrogen group and add the carbon containing group that's present in your alcohol molecule, and you would get the structure of the product. Okay, two ways of thinking about it. And I guess the simpler way is to just think about it as replace that hydrogen with the carbon containing group in your alcohol molecule. Important point to note though is that you want to maintain the connectivity in your alcohol. The carbon that's connected to the oxygen in your alcohol, or the alpha carbon in your alcohol, must connect to that oxygen in the ester, but that would be the product that we would get. So that will be ethyl benzoate. That would be our product. The second example over here, I have a molecule which has both a carboxylic acid group and an alcohol group within the same molecule, and we are reacting it with an ester. In this particular case, the oxygen again, here, the ester oxygen, if you work on it mechanistically, the ester oxygen would get connected to the acyl carbon in your product. Okay, so if we look at it overall from the acyl carbon to the ester oxygen, we are looking at 6 atoms. So our product would be a 6-membered ring, cyclohexane, that's connected to another 6-membered ring. So starting from here, we have 1, 2, 3, 4, 5, and 6. So that will be our product. So it would give us a cyclic ester, an ester molecule where the reaction happened within the molecule, okay? The alcohol was within the molecule, the carboxylic acid was within the molecule. They basically formed a bond. So you get an ester molecule that's cyclic in nature. The third example here, we have a carboxylic acid, 1, 2, 3, 4. So it's a butanoic acid, reacting it with benzyl alcohol. So the product that we get here would be benzyl butanoate, okay? So oxygen here should connect to the alpha carbon of your alcohol. So oxygen connects to the alpha carbon, and there we have our benzene ring. So those are some solved examples of how would you put down or write down the structures of the products from a Fischer esterification reaction.